And now in this lecture we'll answer two questions. In the first question, we find out the size of this angle APC is equals to x. We have to find out the value of this angle, angle x. And in the second question, we find out the length of line segment CD is equals to x. So we have to find out the value of line segment x is equals to CD. So we start with the first question. In the drawing, we have a triangle ABC. This is angle ABC. This is equals to 15 degrees in size. This is angle ACB. This is equals to 13 degrees in size. We know that BP equals to PC. And our task is to find out the size of this angle APC equals to x degrees. We have to find out the value of angle x. So first of all, because of the fact that BP equals to PC, if we define the graph of BP as A, then the graph of line segment PC must be also equal to A because they are equal to each other. In the next step, we will do a construction. That is to say, we'll extend side CA of this triangle ABC by a straight line. And we'll do another construction. That is to say, at point B, we will create angle of 15 degrees in such a way that side BA will be one leg of the angle that we will build, and the other leg will be created in such a way that it will create 15 degrees with this leg BA. So this angle equals to 15 degrees in size according to our construction. The next step, we'll extend this leg by a straight line until it touches the extended side CA. And we'll define the touching point of the extended side CA with this extended leg. This point is point M. By doing this construction, we created the associated triangle BMC. Triangle BMC is an associated triangle because of the fact that those two angles are both equal to 30 degrees in their sizes, and therefore they are equal to each other. So here you can implement rule 20 in this associated triangle BMC. So repeat quickly on rule 20. According to rule 20, the perpendicular to the base of an associated triangle bisect the base. In the drawing, we have triangle BAC. Triangle ABC is an associated triangle because AB equals to AC. And we know that, of course, BC is the base of this associated triangle ABC. According to this rule 20, the perpendicular AD to the base BC bisects the base BC. That is to say, the perpendicular AD divides the base BC into two halves. The first half is BD, and it is of course equals to the second half DC, and each half equals to BC over 2 because of the fact that BC is being bisected. So BD equals to DC equals to BC over 2. So we can actually implement all 20 in our drawing. In our drawing, this is the associated triangle BMC. BC is the base of this associated triangle. So the perpendicular from point M to the base BC bisect the base BC, according to all 20. Well, the perpendicular from point M will touch the base BC. Actually, the perpendicular from point M will touch the base BC at point P. Why? Because at point P, the base BC is being bisected. The first half is BC that equals to A, and the second half is PC that is also equals to A. Therefore, the perpendicular from point M to the base BC will touch the base BC at point P and not in any other point. So MP is perpendicular to the base BC, so this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. In the next step, we'll focus on this right triangle BMP. This right triangle BMP, it is very easy to see that sin 30 degrees equals to MP over MB. So I write it down. This right triangle MBP. Sin 30 degrees equals to MP over MB. And again, in the right triangle MBP, it is very easy to see that sin 30 degrees equals to MP over MB. In the next step, we define the hypotenuse MB as 2B. So sin 30 degrees equals to MP over MB. MB is 2B according to our definition, so we solve MB by 2B. So to that we can find out that sin 30 degrees equals to MP over 2B. Sin 30 degrees is 1/2, so we substitute sin 30 degrees by 1/2. So 1/2 equals to MP over 2B. Here we multiply this equation by 2B, and we get that (2b over 2) equals to MP. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. And we're left only with B equals to MP. Well, we found out that MP equals to B. So in conclusion, you can say that if the hypotenuse MB equals to 2B, then the perpendicular MP must be equal to B. Write it down. MP equals to B. In the next step, we'll focus on this associated triangle BMC. In this associated triangle BMC, line segment AB is the angle bisector of angle MBC. Why? Because of the fact that line segment AB bisects angle MBC into two halves, each half equals to 15 degrees in its size. So we can write down that in the associated triangle MBC, AB is the angle bisector of the associated triangle MBC. So write it down. In the big associated triangle MBC, AB is the angle bisector of angle MBC in the associated triangle MBC. And therefore, according to Rule 19, that is also defined as angle bisector theorem. Angle bisector AB divides the sides of this triangle MBC proportionally. So according to angle bisector theorem, this is also defined as Rule 19. Angle bisector AB divides the sides of the associated triangle MBC proportionally. That is to say, MB over BC, MB over BC equals to MA over AC. So I paste quickly on Rule 19. That is also defined as angle bisector theorem. So according to angle bisector theorem, this is also defined as Rule 19. We know that AD is the angle bisector of angle BAC in this triangle ABC. Why it is angle bisector? Because it divides angle BAC into two halves, each half equals to theta. And because of the fact that AD is angle bisector of this triangle ABC, angle bisector AB divides the sides of this triangle ABC proportionally. That is to say, BD over DC equals to BA over CA. Again, because of the fact that AD is angle bisector of this triangle ABC, angle bisector AD divides the sides of this triangle ABC proportionally. That is to say, BD over DC equals to BA over AC. So if we already implemented all the angle bisector theorem in our drawings. Why? Because, as I mentioned before, the associated triangle BMC, AB is the angle bisector of angle MBC because it bisects angle MBC into two halves, each half equals to 15 degrees each side. And because of the fact that AB is the angle bisector of the associated triangle MBC, angle bisector AB divides the sides of this triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. Again, AB is the angle bisector of triangle MBC, and therefore angle bisector AB divides the sides of triangle MBC proportionally. That is to say, MB over BC equals to MA over AC. MB equals to 2B. So we'll substitute MB by 2B. Over BC. BC equals to A plus 8, that is 2A. And it is equals to MA over AC. So in total, we found out that according to angle bisector theorem, in the associated triangle MBC, the following equation is true. Or we can say that the size of the associated triangle MBC divided proportionally. That is to say, 2B over 2A equals to MA over AC. We have 2 in the numerator, 2 in the denominator, so 2 get cancelled. And we have to leave B over A in this side of the equation is equal to MA over AC. But again, we found out in total that according to angle bisector theorem, B over A equals to MA over AC. In the next step, we will focus on this right triangle MPC. In the right triangle MPC, line segment AP, here LS is abbreviation for line segment AP divides the sides of this triangle MPC proportionally. Divides the sides of the right triangle MPC proportionally. Why? Because we only found out that B over A equals to MA over AC. B over A equals to MA over AC. For that reason, line segment AB divides the sides of this right triangle MPC proportionally. And therefore, line segment AP is the angle bisector of this triangle MPC. And therefore, line segment AP is the angle bisector of the right triangle MPC. And this is according to the converse rule of angle bisector theorem. That is also defined as rule 21. According to converse theorem of angle bisector theorem. It is also defined as rule 21. Repeat again. Because of the fact that if you focus on this right triangle MPC, AP divides the size of this right triangle MPC proportionally. That is to say, we know that B over A equals to MA over AC, and therefore last right AP is the angle bisector of this triangle MPC. According to the converse rule of the converse theorem of angle bisector theorem, that is also defined as rule 21. So repeat quickly on the converse rule. This is the converse rule or converse theorem of angle bisector theorem. It is also defined as rule 21. So repeat quickly on converse theorem on the converse theorem of angle bisector theorem. That is also defined as rule 21. So according to the converse theorem of angle bisector theorem, here in the moment we have triangle ABC. So if we know that line side AD divides the side of this triangle ABC proportionally, that is to say, we know that BD over DC equals to AB over AC, then line side AD is the angle bisector of this triangle ABC. So why rule 21 is the converse rule of rule 19? According to rule 19, angle bisector theorem, if AD is the angle bisector of this triangle ABC, then divides the side of this triangle ABC proportionally. The converse rule to rule 19 is rule 21. Here we know that line side AD divides the sides of this triangle ABC proportionally, and therefore line side AD is the angle bisector of this triangle ABC. So according to the converse rule of converse theorem, according to the converse rule of angle bisector theorem, because of the fact that line side AP divides the sides of this triangle ABC proportionally, line side AP is the angle bisector of this triangle MPC. So if AP is the angle bisector of this triangle MPC, it means that it divides angle MPC into two halves. So the size of angle MPC is 90 degrees. And angle bisector AP divides angle MPC into two halves. So the first half is angle MPA. This is of course equal to 90 degrees over 2, that is 45 degrees. And the second half of the big angle MPC, that is right angle, it is angle APC, that is equal to X, so it is equal to 45 degrees in its size. So if you found out that the angle that you are looking for in this question, that is angle APC, is also defined, that is also defined as angle X equals to 45 degrees in its size. So write it down. I should have found out that the angle that we are looking for in this question, that is angle APC, that is also defined as angle X, is equal to 45 degrees in size. And that is the answer to the first question. In the next step, I will present you the second question and the answer of the second question of this lecture. The second question, our task is to find out the length of this line segment CD is equals to X. We can say we have to find out the length of line segment X is equals to CD. So in the drawing we have a semicircle. Point O is the center of this semicircle. Line segment OE equals to 5 units in itself. Line segment OE equals to 5 units in itself. This is line segment EB. That's equals to 4 units in itself. In addition, we know that those two angles are both right angles. And finally, we know that PQ equals to CQ equals to QE. So if we define the length of PQ as A, then CQ and QE must be also equal to A, each of them, because of the fact that they are equal to each other according to what is given as a question. In the next step, we'll join point C and P together by straight line. By joining point C and P, we created the right triangle CPQ. We have the rule that states that in front of equal sides in the triangle there are equal angles. I repeat again, in front of equal sides in the triangle there are equal angles. So in this right triangle CPQ, in front of those two equal sides, we have those two angles that must be also equal to each other and their sizes. So if we define the size of this angle as alpha, then the size of this angle must be also equal to alpha because they are equal to each other according to the rule that I mentioned. We know that the sum of the angles in any triangle is equal to 180 degrees. So the right triangle CPQ, alpha plus alpha, that is 2 alpha plus 90 degrees, in total must be equal to 180 degrees. So maintenant, in the right triangle CPQ, two alpha plus 9 degrees, in total must be equal to 180 degrees. According to the rule, that the sum of the areas in any triangle is equal to 180 degrees. Here we subtract 90 degrees from this equation, and finally we get that 2 alpha equals to 180 degrees minus 90 degrees is 90 degrees. So 2 alpha equals to 90 degrees. Here we will divide this equation by 2 and finally get that the missing angle alpha is equal to 90 degrees over 2 is 45 degrees. Those two angles are both equal to alpha, and therefore each of them is equal to 45 degrees in its size. So, written down. So actually, triangle CPQ is a right triangle because this is a right angle, and it is also an associated triangle because of the fact that those two sides are equal to each other. Therefore, we can say that triangle CPQ is simultaneously a right triangle and also an associated triangle. So in general, we can say that in a right triangle that is also an associated triangle, we will always have the same three angles. One angle must be a right angle, and the other two angles, each of them must be equal to 45 degrees in their sizes. This is true for any right angle that is also an associated triangle. It's given us a question that CE is a straight line. So if you focus on the upper side of the straight line CE at point Q, here the sum of the angles must be equal to 180 degrees according to rule 3. Rule 3 states that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at the upper side of the straight line CE at point Q? We have this angle that is a right angle, plus this missing angle, so that the sum of those angles must be equal to 180 degrees according to rule 3. Therefore this missing angle must be equal to 90 degrees in its size. In the next step, we will join points P and E together by a straight line. By joining points P and E, we created the right triangle PQE. In the right triangle PQE, those two sides are equal to each other. Each of them equals to A, and therefore they are equal to each other. And therefore the right triangle PQE is also an associated triangle. Those two sides are equal to each other. And therefore, those two missing angles must be equal to 45 degrees in each of them, according to the rule that I mentioned, that in any right triangle that is also an associated triangle, we always have the same three angles. One angle is the right angle, and the other two angles, each of them must be equal to 45 degrees in its size. So this angle equals to 45 degrees in its size, and this angle also equals to 45 degrees in its size. In the next step, we will complete this semicircle to a circle. We'll convert the semicircle to a circle, and then we will extend side CE by a straight line until it touches the circle. We will define the touching point of the extended side CE with this circle. This point is point M. Likewise, we'll extend side CO by a straight line until it touches the circle. And we will define the touching point of the extended side CO with this circle. This point is point N. In the next step, we join points M and then together by a straight line. Here we extended also side PE by a straight line and it touches the circle. And we find the touching point of the extended side PE with this circle. This point is point N. And we also extended, we joined points C and D together by a straight line. In the next step, we join points M and N together by a straight line. This is triangle CPN. Again, this angle is defined as triangle CPN. Triangle CPN equals to 45 degrees plus 45 degrees is 90 degrees. It is a right angle. And triangle CPN subtend on chord CN. So here we can implement rule 5 in our drawing. Please click on rule 5. According to rule 5, any triangle that equals to 90 degrees inside must subtend on the diameter of the circle. In the drawing, you have a circle. This is triangle MAN. We know that triangle angle MAN is a right angle, it is equal to 90 degrees inside, and therefore according to this rule, rule 5, triangle MAN must subtend on the diameter of the circle. Triangle MAN subtend on chord MN, that is the diameter of the circle. So according to rule 5, any triangle that is equal to 90 degrees inside, that, like this angle, must subtend on the diameter of the circle. So we can implement rule 5 in our drawing. Why? Because this is triangle CPN, equals to 90 degrees inside, it is a right angle, and therefore it must subtend on the diameter of the circle. Triangle CPN subtend on chord CN, therefore according to rule 5, chord CN must be the diameter of the circle. Okay, now this is chord CN, that is the diameter of the circle according to rule 5. The next step, we will implement the converse rule of rule 5, that is rule 7. This triangle CMN. This is triangle CMN. It is very easy from the drawing to see it from the drawing that triangle CMN subtend on chord CN, that is the diameter of the circle. Therefore, according to the converse rule of rule 5, that is rule 7, Triangle CMN that subset of the diameter of the circle must be equal to 9 degrees in its size. So first click on rule 7. According to rule 7, if a peripheral angle subtend of the diameter of the circle, then it is equal to 90 degrees in its size. The moment we have a circle, this is peripheral angle ACB, and we know that peripheral angle ACB subtend of the diameter of the circle. That is to say, called AB, that is the diameter of the circle, and therefore according to this rule 7, peripheral angle ACB must be equal to 90 degrees in its size. So according to rule 7, any peripheral angle that subtend on the diameter of the circle, like this peripheral angle, must be equal to 90 degrees in its size. So we can implement rule 7 in our drawing. When I put in our drawing, as I mentioned before, this is peripheral angle CMN, the subtend on the diameter of the circle, therefore it must be equal to 90 degrees in its size. According to rule 7. So why rule 5 is the converse rule of rule 7, or why rule 7 is the converse rule of rule 5? Because according to rule 5, if we know that a peripheral angle is equal to 90 degrees inside, then it must subtend on the diameter of the circle. And according to the converse rule of rule 5, this is rule 7, if we know that the peripheral angle subtend on the diameter of the circle, then it must be equal to 90 degrees in its size. Okay, so rule 7 is the converse rule of rule 5. Those two angles are defined as vertex angles. We know that vertex angles are equal to each other. But this angle is 45 degrees, and therefore this angle must be also equal to 45 degrees inside according to the rule that I mentioned. Vertex angles are equal to each other. So in this small triangle EMN, this angle equals to 45 degrees in its side, this angle is a right angle, and therefore this missing angle must be equal to 45 degrees in its side, according to the rule that said that the sum of the angles in any triangle is equal to 180 degrees. What is the radius of this circle? Actually, the radius of any circle, we know that point O is the center of the circle. It is given as a equation that point O is the center of the circle. The radius of any circle starts from the center of the circle, this will say point O, and then on a point that is located on the circle itself. Point B is located on the circle itself. Therefore, point B is the radius of this circle. What is the length of 4B? OB equals to OE, that is 5, plus EB, that is 4. So in total, the radius of B equals to 5 plus 4, that is 9. So actually found out that the radius of this circle is equal to 9 units in its length. ON is also the radius of this circle, therefore it is equal to 9 units in its size, and to 9 units in its length. Likewise, OA is also the radius of the circle, it is equal to 9. And finally, CO is also the radius of this circle, it is equal to 9. In the next step, we find out the area of this green triangle, COE. Repeat again, we find out the area of this green triangle, COE. What is the area of this green triangle, COE? Actually, we know that the area of any triangle equals to the base of the triangle times the height to the base over 2. So, we will choose the base of this green triangle COE as CO. The base is CO according to our choice times the height. The height to the base CO must rest with the base CO. You can say also that the height to the extended base CO must rest with the extended base. CO is the base, therefore the extended base is CN. So the height to the base must rest 90 degrees with the extended base CN. So just go perpendicular from point A to CN, and the perpendicular will be the height to the base because it's greater 90 degrees with the base CN, with the extended base CN. So from point A we'll do perpendicular on the extended base CN. So this angle equals to 90 degrees inside, and this angle also equals to 90 degrees inside according to our construction. We define the touching point of the perpendicular from point A and CN. This point is point G. And we define the length of EG as H. So as I mentioned before, H is the height to the extended base CN. Therefore, the height of the green triangle COE, the green triangle COE, is H, because it's greater than degrees with the extended base CN. So the height is H over 2. So in total, we should find out that the area of the green triangle COE is equal to 9H over 2 square units in its size. Likewise, we find out the area of this lower triangle OEN. What is the area of this lower triangle OEN? So we know that the area of any triangle equals to the base of the triangle times the height to the base or the height to the extended base, doesn't matter, over 2. We'll choose the base of this lower triangle OEN as ON. And the height to the base ON must rest 90 degrees with the base ON. H definitely rests 90 degrees with the base ON. So the height is H. Get 90 degrees with the base. This angle equals to 90 degrees, this angle also equals to 90 degrees. So the height is H over 2. H over 2. So in total we should find out that the area of this lower triangle ON equals to ON. ON is the radius of the circle, this equals to 9. Times the height to the base is H over 2. So in total, we actually found out that the area of this lower triangle OEN is equal to 9H over 2 square units in its size. Exactly like the area of the green triangle COE, that is also equals to 9H over 2 square units in its size. Therefore, the area of the green triangle COE equals to the area of the lower triangle OEN. So, right now, in total, we should find out that the area of the green triangle COE equals to the area of the lower triangle OEN. So, right now, the area of the green triangle COE equal to the area of the lower triangle OEN. What is the area of the big triangle CEN? This is the big triangle CEN. What is the area of this big triangle CEN? The area of the big triangle CEN must be equal to the sum of the areas of the two components that is consist of. The big triangle CEN consists of those two components. The first component is the green triangle COE. So the area of the first component is the area of the green triangle COE plus the area of the second component that the big triangle CN consists of. The second component is the lower triangle OEN. So it is the area of the lower triangle OEN, that is the area of the second component that the big triangle CN consists of. So in total we found out that the area of the big triangle CN equals to the area of the green triangle COE plus the area of the lower triangle OEN. But we only found out that the area of the lower triangle OEN equals to the area of the green triangle COE. So we can substitute the area of the lower triangle OEN by the area of the green triangle COE because they are equal to each other in their sizes. So in total we found out that the area of the big triangle CN equals to the area of the green triangle COE and the area of the lower triangle ON equals to the area of the green triangle COE. So we solve the area of the lower triangle ON by the area of the green triangle COE. So in total we should find out that the area of the big triangle CN equals to the area of the green triangle COE plus the area of the green triangle COE, that is to say it is 2 times the area of the green triangle COE. So in total we should find out that the area of the big triangle CEN is twice as large as the area of the green triangle COE. Here we will divide this equation by 2. And finally we get that the area of the green triangle COE is half of the area of the big triangle CN. But again, found out of it that the area of the green triangle COE is half of the area of the big triangle CN. In the next step, we will find out the area of this big triangle CN according to the rule that says that the area of any triangle equals to the base of the triangle times the height of the base over 2. So the area of the big triangle CEN is equal to the base of the triangle times the height to the base of the extended base, doesn't matter, over 2. We'll choose the base of this big triangle CEN as CE. CE is the base according to our choice. And the height to the base or the height to the extended base must get 90 degrees with the extended base. CE is the base and therefore the extended base is CM. So the height to the base must get 90 degrees with CM. Here NM definitely gets 90 degrees with CM. This is right again. So the height is NM. 9 to the extended base is nm over 2. So the area of the big triangle CN equals to the base CE times the height nm over 2. We have the rule that says that in front of equal angles in the triangle they are equal size. Again, in front of equal angles in the triangle they are equal size. So if you focus on this right triangle E and M, in front of those two equal angles we have those two sides that must be also equal to each other in their length. So if we define the length of this side EM as B, then the length of side MN must be also equal to B according to the rules that I mentioned. In front of equal angles in the triangle they are equal size. So in total we should find out that MN equals to B means in its length. The area of the big triangle CMN equals to CE times NM over 2. CE in total equals to CQ, that is A, plus QE, that is also A. So C in total equals to A plus A, that is 2A. Times NM. We just find out that NM equals to B. Divided by 2. We have 2 in the numerator, 2 in the denominator, so 2 in the denominator, so 2 will get cancelled. And we left only with A times B. So in total we should find out that the area of the big triangle CEN is equal to A times B square in size. We already found out that the area of the great triangle COE is equal to the area of the big triangle CN over 2. But the area of the big triangle CN is AB. So we can write here that the area of the big triangle is AB divided by 2. So in total we should find out that the area of the green triangle COE equals to A times B over 2 square in size. Repeat again, the area of the big triangle CEN is equal to A times B square in size, while the area of the green triangle CO equals to A times B over 2 square in size. The area of the green triangle COE is equal to A times B over 2 square in size. In the next step, we will implement Rule 65 in our drawing. Rule 65 is about two chords that intersect with each other inside the circle. So I'll repeat quickly on Rule 65. According to Rule 65, first of all, Rule 65 is true in any circle, so this circle could be any circle. So in any circle, if chord AB intersects with chord CD at point O, then the following equation is true. AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So you can implement Rule 65 in our drawing. In our drawing, this is chord AB that intersects with chord CM at point E. Again, chord AB intersects with chord CM at point E. The intersection point between chord AB and chord CM occurs at this point, point E. So actually all the requirements for full 65 are satisfied, and therefore we can implement our drawing all 65. So write it down. Now we're drawing. Chord AB intersects with chord CM, it's pointy. Therefore, according to rule 65, the following equation is true. AE times EM and AE times EB is equal to CE times EM. According to rule 65. And again, chord AB intersects with chord CE. Chord AB intersects with chord CM at point E. Therefore, according to rule 65, the following equation is called AE times EB equals to AE times EB equals to CE times EM. AE times EB equals to CE times EM. AE equals to AO plus OE. AO is the reduce of the circle, that is 9, plus OE, that is 5. So in total, A equals to 9 plus 5 is 14. AE is 14. Times EB. EB equals to 4 units in itself, according to what is given as the question. So in this side of the equation, we have 14 times 4. Is equals to CE equals to CQ, CE equals to A plus A, that is 2A. Again, C equals to CQ, that is A, plus QE, that is A. So in total, CE equals to A plus A, that is 2A. C equals to 2A. Times EM. EM equals to B units in itself according to our definition. M equals to B. So in total, we should found out that 14 times 4 equals to 2AB. 14 times 4 is 56. So 56 equals to 2AB. Here we divide this equation by 2. And finally we get that 56 over 2 is 28 equals to 2AB over 2 is AB. So in total we found out that A times B equals to 28. A times B equals to 28. We already found out that the area of the big triangle CN equals to A times B. The area of the big triangle CEN equals to A times B squared in its size. But we just right now found out that AB equals to 28, so we can write that AB equals to 28, and from those two sides of the equation are equal to each other. That is to say, we actually found out that the area of the big triangle CN is equal to 28 squared in its size. Likewise, we already found out that the area of the triangle CO equals to AB over 2. The area of the green triangle COE is equal to A times B over 2 coordinates inside according to what we already found out. But AB is 28, so we can write here that AB is 28 over 2. 28 over 2 is 14. Those two sides of the equation are equal to each other. So in total, we found out that the area of the green triangle COE equals to 14 coordinates in size. The area of the green triangle COE is equal to 14 coordinates in size. In the next step, we will calculate the area of this right triangle COE according to the rule that says that the area of any triangle equals to the base of the triangle times the height to the base over 2. So the area of the green triangle COE is equal to the base of the triangle times the height to the base of the extended base over 2. We'll choose the height of this the base of this green triangle COE is OE. OE is the base of the green triangle COE according to our choice times the height. The height to the extended base OE is EA. Again, EA is the height to the extended base OE. CD definitely creates like the rest with EA. Therefore, CD is the height of the extended base. The height is CD over 2. So in total, we found out that the area of the green triangle COE equals to the base OE times the height CD over 2. OE equals to 5 units in itself according to what is given as the question. OE equals to 5 times CD. CD equals to X. X is the line segment that we are looking for. So we substitute CD by X. Divided by 2. Those two sides of the equation are equal to each other. So in total, we actually found out that the area of the green triangle COE is equal to 5x over 2 squared in its size. But we already found out that the area of the green triangle COE equals to 14 squared in its size. So we can agree that the area of the green triangle COE equals to 14 square units in its size. Those two sides of the equation are equal to each other. That is to say, 14 equals to 5x over 2. So 14 equals to 5x over 2. Here we will multiply this equation by 2 and get that 2 times 14 is 28 equals to 5x. Here we will divide this equation by 5 and finally get that x actually equals to CD, of course. So CD is equals to x is equal to 28 over 5 28 over 5 units. Instead, from terms of numbers, 28 over 5 is 5.6 units in its name. So the answer to the question, to the second question, is that the length of line segment CD is equal to x. This is equal to either 28 over 5 units in its length. From terms of numbers, CD is equal to x is equal to 5.6 units in its length. So finish to answer the second question. The next step, I'll summarize the lecture. We start with the repetition of the solution of the first question, and then we repeat on the solution of this second question. In the first question, our task was to find out the size of this angle APC that is equal to x. So we have to find out the value of angle x. So in the drawing, we have angle ABC, BP equals to PC. This is angle ABC, this equals to 15 degrees in size. This is angle ACB, this equals to 40 degrees in size. Again, our task is to find out the size of this angle APC, it is equal to x. So we have to find out the value of this angle x. So first of all, BP equals to PC. So if we find the length of line segment BP is A, then the length of line segment PC must be also equal to A, because they are equal to each other. Repeat again. BP equals to PC, and each of these line segments are equal to A units according to our definition. The next step, we did a construction, that is to say we extended side CA of this triangle ABC by a straight line. Then we did another construction, that is to say at point B we created angle of 15 degrees in the following way. Side BA is the first leg of the angle that we create, and the second leg that we will create creates 90 degrees with the leg BA. So this angle equals to 15 degrees inside according to our construction. The next step, we extended this leg by straight line until it touches the extended side CA, and we define the touching point of the extended side CA with this extended leg. This point is point M. By doing this construction, we created the associated triangle BMC. Triangle BMC is an associated triangle because of the fact that those two areas are both equal to 30 degrees in size. They are sided, and therefore they are equal to each other. Therefore, triangle BMC is an associated triangle. So here you can implement all 20 that is about associated triangle. Please click on rule 20. In the drawing we have the associated triangle ABC. ABC is an associated triangle because AB equals to AC. So according to rule 20, and BC is of course the base of this associated triangle ABC. So according to rule 20, the perpendicular to the base of an associated triangle bisects the base. So the perpendicular AD to the base BC bisects the base BC. First of all, those two angles are both equal to 90 degrees according to our construction, because AD is the perpendicular to BC, the base BC. According to this rule 20, the perpendicular AD to the base BC bisects the base BC. That is to say, it divides the base BC into two halves. The first half is BD, and it is of course equals to the second half DC. Each half equals to BC over 2 because BC has been bisected. So in total, we found out that the perimeter AD to the base BC bisect the base BC. That is to say, BD equals to DC equals to BC over 2. So we can implement rule 20 in our drawing, or put in our drawing. This is the associated triangle ABC. The perimeter from point M to the base BC bisect the base BC. If the perimeter from point M bisects the base BC, it means it divides the base BC into two halves. The first half. So where the perpendicular from point M will touch the base BC, the perpendicular from point M must touch the base BC at point P and not in any other point. Why? Because at point P is the midpoint of BC. Why point P is the midpoint of BC? Because at point P, the base BC has been bisected. The first half is BP, this is A. The second half is PC, this is also A. So the perpendicular from point M to the base BC must touch the base BC at its midpoint, that is point P. So MP is the perpendicular to the base BC, and therefore this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. So the perpendicular MP bisects the base BC. So the first half is BP, and this is of course equals to the second half BC. Each half equals to BC over 2. BP equals to A, and PC also equals to A. So in the next step, we focus on this right triangle BMP. The right triangle BMP is very easy to see that sinus 40 degrees equals to MP over MP. And again, in the right triangle BMP, sinus 40 degrees equals to MP over MP. We find the length of MP is 2B, and therefore sinus 40 degrees equals to MP over MP. MP is 2B. So sinus 40 degrees equals to MP over 2B. Sinus 40 degrees is 1 half, so 1 half equals to MP over 2B. Here we multiply this equation by 2B, and finally found out that MP equals to 2B over 2. We have 2 in the denominator, so 2 will get cancelled. So here we left only with B. So MP equals to B. In conclusion, we can say that if the hypotenuse MP equals to 2B, then the perpendicular MP must be equal to B. So the perpendicular is twice as long, and the hypotenuse the perpendicular is twice as long as MP. Actually, the hypotenuse MB is twice as long as the perpendicular MP. Okay? So, in the next step, we focus on this big associated triangle BMC. This big associated triangle BMC, AB bisect angle MBC. Why? Because AB divides angle MBC into two halves. The first half is 15 degrees and the second half is 15 degrees. So, in the big associated triangle MBC, AB is the angle bisector. And again, we found out that in the big associated triangle MBC, AB is the angle bisector of triangle MBC. Therefore, we can implement here angle bisector theorem that is also defined as Rule 19. So I can quickly on angle bisector theorem. According to angle bisector theorem, if AD is the angle bisector of this triangle ABC, then it divides the sides of this triangle ABC proportionally. That is to say, DB over DC equals to AB over AC. And again, according to angle bisector theorem, if AD is the angle bisector of this triangle ABC, then it divides the sides of this triangle ABC proportionally. That is to say, DEB over DC equals to AB over AC. What does it mean that AD is angle by circle? It means it divides angle BAC into two halves. Each half equals to theta. So we can implement the angle by circle theorem in our drawing. In our drawing, so as I already mentioned before, AB is the angle by circle of this triangle ABC. Therefore, angle by circle AB divides the sides of this triangle ABC proportionally. That is to say, MB over BC equals to MA over AC. Repeat again, because of the fact that AB is the angle by circle of triangle ABC, divides the sides of this triangle ABC proportionally. That is to say, MB over BC equals to MA over AC. According to the converse theorem of angle by circle theorem. It is true actually according to the angle by circle theorem. It is true according to angle by circle theorem. So, according to angle by circle theorem, that is also defined as rule 19. Angle by circle AB divides the sides of triangle ABC proportionally. That is to say, MB over BC equals to MA over AC. MB over BC equals to MA over AC. MB is 2B, BC is A plus A, that is 2A. And it's equals to MA over AC. And again, MB is 2B and BC is 2A, and this is equals to MA over AC according to angle by circle theorem. We have 2 in the numerator, 2 in the denominator, so 2 get cancelled. So in this side of the equation we left only B over A equals to MA over AC. So in total we found out that B over A equals to MA over AC. This is according to angle by circle theorem. In the next step, we focus on this right triangle MPC. The right triangle MPC, it is very easy to say that line side AP divides the sides of this triangle MPC proportionally. That is to say, we only found out that B over A equals to MA over AC. Again, B over A equals to MA over AC. Therefore, line side AP divides the sides of this triangle MPC proportionally. Therefore, according to the converse rule of angle by circle theorem, line side AB must be the angle by circle of this triangle MPC. So, basically, on the converse theorem of angle by circle theorem, that is also defined as rule 21. According to the converse theorem of angle by circle theorem, if we know that line side AD divides the sides of this triangle ABC proportionally, that is to say, we know that DEB over DC equals to AB over AC. Then, line side AD is defined as angle by circle of this triangle ABC. Okay. So we can implement the converse theorem of angle by circle theorem in this right triangle MPC. Well, we know that line side AP divides the sides of this triangle MPC proportionally. That is to say, we know that B over A equals to MA over AC. Therefore, according to the converse rule of angle by circle theorem, line side AP must be the angle by circle of this triangle MPC. Repeat again. according to the converse theorem of Engel-Basserto theorem, that is also defined as Rule 21, in the right triangle MPC, line segment AP divides the size of this triangle MPC proportionally. That is to say, we know that B over A equals to MA over C. We know that B over A equals to MA over AC. Therefore, according to the converse theorem of Engel-Basserto theorem, line segment AP must be the Engel-Basserto of this triangle MPC. Okay. Line segment AP is the Engel-Basserto of this triangle MPC. Repeat again. Therefore, line segment AP is the Engel-Basserto of this triangle MPC. According to the converse theorem of Engel-Basserto theorem. So if AP is the Engel-Basserto of triangle MPC, it means that it divides angle MPC into two halves. Each half must be equal to 90 degrees over 2, that is 45 degrees. The first half is angle MPA, that is also 45 degrees this side. The second half of angle MPC is angle APC, that is also defined as angle X, that is also 45 degrees in its size. So in total, we found out that the angle that we are looking for in this question, that is angle APC, is also defined as angle X equals to 45 degrees in size. So we finish. Repeat again. Why Rule 21 is the converse rule of Rule 19. According to Rule 19, that is also defined as Engel-Basserto theorem. If AD is Engel-Basserto of triangle ABC, then it divides the size of this triangle ABC proportionally. While according to the converse rule of Rule 19, if we know that line segment AD divides the size of this triangle ABC proportionally, then AD is the Engel-Basserto of triangle ABC. So here we know that AD is the Engel-Basserto, and therefore divides the size of this triangle ABC proportionally. While here we know that line segment AD divides the size of this triangle ABC proportionally, therefore line segment AD is the Engel-Basserto of this triangle ABC. So Rule 21 is the converse rule of Rule 19. So in the next step, we will repeat on the solution of the second question of this lecture. The second question, our test, is to find out the length of this line segment CD equals to X. So instead that our test is to find out the length of line segment X is equal to CD. In the drawing, we have a semicircle. Point O is the center of this semicircle. Line segment O equals to 5 units in its length. Line segment EB equals to 4 units in its length. Those two angles are both right angles. We know that CQ equals to PQ equals to QE. So if you find the length of PQ as said, then CQ and QE must be also equal to each of them because of the fact that they are equal to each other. Then again, PQ equals to CQ equals to QE. In the next step, we join point C and P together by straight line. By joining point C and P, we can get the right triangle CQP. The right triangle CQP, we have the rule that sets in the front of equal sides in the triangle, there are equal angles. Again, in front of equal sides in the triangle, there are equal angles. So in front of in the right triangle CQP, in front of those two equal sides, we have those two angles that must also equal to each other and their sizes. So if you find the size of this angle as alpha, then the size of this angle must be equal to alpha according to the rules that I mentioned. You also know that the sum of the angles in any triangle equals to 180 degrees. So in the right triangle CQP, alpha plus 9 degrees, the total must be equal to 180 degrees. So again, the right triangle CQP, the sum of the angles must be equal to 180 degrees. So 2 alpha plus 9 degrees equals to 180 degrees. If subtracted 90 degrees from this equation, and finally found out that 2 alpha equals to 180 degrees minus 90 degrees, it's 90 degrees. So 2 alpha equals to 90 degrees, here we divide this equation by 2, and finally found out that the missing angle alpha equals to 45 degrees in its size. So those two angles are both equal to alpha, and therefore each of them is equal to 45 degrees in its size. So actually can conclude that if a triangle is simultaneously an associated triangle is also a right triangle, like this triangle CPQ. CPQ is a right triangle because of the fact that this is a right triangle. CPQ is an associated triangle because of the fact that those two sides are equal to each other. So triangle CPQ is a right triangle and also associated triangle simultaneously. So we can say in general that in any right triangle that is also an associated triangle, we will always have the same three angles. One angle is a right angle, the other two angles, each of them must be equal to 45 degrees in its size. This is true in any right triangle that is also an associated triangle. It's given us the question that CE is a side line. So if you focus on the upper side of the side line CE at point Q, if the sum of the angles must be equal to 180 degrees according to all three. All three said that the sum of the angles from one side of the side line is equal to 180 degrees. So which angles we have at the upper side of the side line CE at point Q? We have this angle that is right angle plus this missing angle. Total the sum of those two angles must be equal to 180 degrees according to all three. Therefore this missing angle must be equal to 90 degrees in size. In the next step we join points P and E together by side line. By joining points P and E, we get the right triangle PQE. The right triangle PQE is also an associated triangle because of the fact that those two sides are equal to each other. Each of them is equal to A, therefore they are equal to each other. So triangle PQE is an associated triangle and also a right triangle simultaneously. So this is a right angle. Those two right angles must be equal to 45 degrees in their sizes, each of them. Okay. So in the next step, I completed this semicircle to a circle, and then we extended side PE by side line until it touches the circle. We define the touching point of the extended side PE with this circle. This point is point N. Likewise, we extended side CE by side line until it touches the circle. We define the touching point of the extended side CE with this circle. This point is point M. In the next step, we join points M and N together by side line, and we also join points C and N together by side line. Here, we have peripherical CPN. This is peripherical CPN. Is equals to 45 degrees plus 45 degrees is 90 degrees. So peripherical CPN is a right angle, and it's subset on chord CN. So here we can implement all 5 in our drawing. Please click on all 5. Only to all 5, any peripherical is equal to 90 degrees inside must subset on the diameter of the circle. And again, if only to all 5, any peripherical is equal to 90 degrees inside must subtend on the diameter of the circle. In the drawing, we have a circle. This is peripherical MAN, and we know that peripherical MAN equals to 90 degrees inside, and therefore according to this, all 5 peripherical MAN must subtend on the diameter of the circle. Peripherical MN subset on chord MN, and indeed chord MN is the diameter of the circle. So according to all 5, any peripherical that is equal to 90 degrees inside must subset on the diameter of the circle. We can implement all 5 in our drawing. Why? Because in our drawing This is periphragal CPN, that is the right angle. Therefore, periphragal CPN must subtend of the diameter of the circle according to rule 5. Periphragal CPN subtend of chord CN, therefore, according to rule 5, periphragal chord CN must be the diameter of the circle. In the next step, we focus on this periphragal CMN. Periphragal CMN subtend of chord CN again. Periphragal CMN is periphragal subtend of chord CN, that is the diameter of the circle. Therefore, according to rule 7, that is the converse rule of rule 5, periphragal CMN must be equal to 90 degrees inside. So I repeat quickly on rule 7. According to rule 7, if a periphragal subtend of the diameter of the circle, then it must be equal to 90 degrees in its size. In the drawing, we have a circle. This is periphragal ACB, and we know that periphragal ACB subtend on the diameter of the circle. Therefore, periphragal ACB must be equal to 90 degrees in its size. So you can actually implement rule 7 in our drawing. I put in our drawing, as I already mentioned before, this is periphragal CMN that subtend on the diameter of the circle, that is to say, called CN, that is the diameter of the circle, therefore it must be equal to 90 degrees in its size, according to rule 7. Repeat again, why rule 7 is the converse of rule 5. According to rule 5, if a periphragal is equal to 90 degrees inside, then it must subtend on the diameter of the circle. But according to rule 7, that is the converse rule of rule 5, if we know that a periphragal subtend on the diameter of the circle, then it must be equal to 90 degrees in its size. Okay. Those triangles don't define as vertex angles, and we know that vertex angles are equal to each other. But this angle equals to 45 degrees inside, and therefore this missing angle must be equal to 45 degrees inside according to the rules I mentioned. This small right triangle EMN, this angle equals to 45 degrees inside, this is the right angle, and therefore this right missing angle must be equal to 45 degrees inside according to the rule that says that the sum of the angles in any triangle is equal to 180 degrees. What is the radius of this circle? Actually, the radius of any circle starts from the center of the circle, that is to say from point O, and that's at any point on the circle itself. Point B located on the circle itself, therefore OB is the radius of this circle. OB in total equals to OE, that is 5, plus EB, that is 4. O in total equals to 5 plus 4, that is 9. So the radius of the circle equals to 9 units in its length. Likewise, the radius CO equals to 9, the radius ON also equals to 9, and the radius AO equals to 9 units in its length. This is the radius of the circle. In the next step, we calculated the area of this green triangle COE according to the rule that said that the area of any triangle equals to the base of the triangle times the height of the base over 2. Repeat again, the area of the green triangle COE must be equal to the base of the triangle times the height to the base over 2. It is the height to the base or the height to the extended base, it doesn't matter. So we choose the base of this green triangle COE as CO, and so the base is CO, so the extended base is CN. The height to the extended base must get with the extended base. So from point E, we go perpendicular on CN, so EG is the height to the base because we get with the extended base CN. We define EG as H, so the height to the base is H because it's greater with the extended base CN. So in total, we found out that the area of the green triangle CO equals to the base, that is CO according to our choice. The height to the extended base is H over 2. So in total, we found out that the area of the green triangle CO equals to 9H over 2 square units in its size. Likewise, we calculated the area of this lower triangle OEN. And the area of the lower triangle OEN equals to the base of the triangle times the height over 2. The area of the lower triangle OEN equals to the base of the triangle times the height to the base over 2. So the base, we choose the base of this triangle OEN lower triangle ON is ON, and the height of the base is H because it's greater than with the base over 2. So in total we should find out that the area of the lower triangle ON equals to the base that is ON times the height that is H over 2. ON is the radius of the circle, that is equal to 9. So we substitute ON by 9, so in total we should find out that the area of the lower triangle ON also equals to 9, H over 2, exactly like the area of the grand triangle COE. Therefore, the area of the grand triangle COE equals to the area of the lower triangle ON. But again, in total we should find out that the area of the grand triangle COE equals to the area of the lower triangle ON. In the next step, we calculated the area of this, we found out the area of this big triangle CN. What is the area of the big triangle CN? What is the area of the big triangle CN? The area of the big triangle CN must be equal to the sum of the areas of those two components that it consists of. The first component is the grand triangle CN, and the second component that it consists of is this lower triangle ON. Therefore, the area of the big triangle CN must be equal to the area of the first component that it consists of, that's actually the area of this grand triangle COE, plus the area of the second component that it consists of, this is actually the area of this lower triangle ON. So in total we should find out that the area of the big triangle CN equals to the area of the grand triangle COE plus the area of the lower triangle ON. But we only found out that the area of the lower triangle ON equals to the area of the grand triangle COE. So we can substitute the area of the lower triangle ON by the area of the grand triangle COE because they are equal to each other. So we substitute the area of the lower triangle ON by the area of the grand triangle COE. So in total we should find out that the area of the big triangle CN equals to the area of the grand triangle COE plus the area of the grand triangle COE, that is to say it is 2 times the area of the grand triangle COE. So in total we should find out that the area of the big triangle CN is twice as large as the area of the grand triangle COE. We divided this equation by 2 and we found out that the area of the grand triangle COE equals to half of the area of the big triangle CN. In the next step, we calculated the area of this big triangle CN according to the rule that the area of any triangle equals to the base of the triangle times the height of the base over 2. The area of the big triangle CN equals to the base of the triangle times the height of the base over 2. We choose the base of this big triangle CN as CE, and the height of the base must create 90 degrees with the extended base CE. The extended base CE is CM, and the extended base C is CM. And M definitely creates 90 degrees with CM, and therefore NM is the height of the base. So the base is C according to our choice, and the height to the extended base is NM over 2. In this small right triangle EMN, we have the rule that sets in front of equal angles in the triangle that are equal sides. So in front of those two equal angles, we have those two sides that must be also equal to each other and their length. So if we define the length of EM as B, then the length of MN must be also equal to B according to the rule that I mentioned. So in total we should find out that MN equals to B. MN equals to B, and CE equals to CQ, that is A, plus QE, that is also A. So in total, C equals to A plus A, that is 2A. But again, we should find out that C equals to 2A, and M equals to B divided by 2. So in total, the area of the big triangle CN equals to 2AB over 2. We have 2 in the numerator, 2 in the denominator, so 2 will get cancelled. We left only with 8 times each. Those two sides of the equation are equal to each other. So in total, we should find out that the area of the big triangle CN equals to 8 times B squared in size. And we already found out that the area of the grand triangle COE equals to the area of the big triangle CN over 2. So for this equation here, we just right now found out that the area of the big triangle CN equals to 8 times B. So in total, the area of the grand triangle CO equals to 8 times B over 2. Because again, in total, we should find out that the area of the big big triangle CA equals to A times B squared in size, and the area of the green triangle CO equals to A times B over 2 squared in size. The next step, implemented rule 65 in our drawing. Quickly on rule 65. According to rule 65, if chord AB intersects with chord CD at point O, then the following equation is to AO times OB equals to CO times OD. Again, chord AB intersects with chord CD at point O. Therefore, this drawing, the following equation is to AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can actually implement rule 65 in our drawing. Why? Because in our drawing, we have chord AB that intersects with chord CM at point A. Again, chord AB intersects with chord CM at point E. So all the requirements of rule 65 are satisfied, and therefore we can implement rule 65. But again, now drawing, chord AB intersects with chord CM at point E. So according to rule 65, the following equation is to AE times EB equals to CE times CM. AE times EB equals to CE times CM. AE equals to AO, that is 9 plus OE, that is 5. 9 plus 5 is 14, so A equals to 14, times EB. EB equals to 4, according to what is given in the question. So EB equals to 4, so in total this side of the equation we have 14 times 4 equals to CE. CE equals to A plus A, that is 2A, plus EM. EM equals to B. So in total, this side of the other side of the equation we have 2A times B. So in total we found out that 14 times 4 equals to 2AB. 14 times 4 is 56 equals to 2AB. Here we divided this equation by 2 and we found out that A times B equals to 28. Okay, again, if we found out that A times B equals to 28, we already found out that the area of the big triangle CA equals to A times B. And again, we found out that the area of the big triangle CA equals to A times B, and the area of the green triangle CO equals to A times B over 2. So I copied those two equations here. We already found out that the area of the big triangle CN equals to A times B, and the area of the green triangle CN equals to A times B over 2. So the area of the big triangle CEN equals to A times B, but A times B equals to 28. So look at this equation here, A times B equals to 28. And from this equation, those two sides of the equation are equal to each other. That is to say, if we found out that the area of the big triangle CA equals to 28 squares in size. We already found out that the area of the green triangle CO equals to A times B over 2. So copy this equation here. The area, according to what we already found out, the area of the green triangle CO equals to A times B over 2 squares in size. AB is 28, so AB is 28 over 2. 28 over 2 is 14. So in total we found out that the area of this green triangle COE equals to 14 squares in size. The next step we calculated the area of this green triangle COE according to the rule that says that the area of green triangle equals to the base of the triangle times the height of the base over 2. The area of the big green triangle COE equals to the base of the triangle times the height of the base over 2. We choose the base of this green triangle COE as OE. In the height to the base must rate 90 degrees with the extended base. The base is EO, so the extended base is EA. CD definitely creates 90 degrees with EA, so CD is the height to the base. And again, the base of triangle COE is OE according to our choice. The height of the extended base is CD divided by 2. So total we found out that the area of the green triangle CO equals to the base OE times the height of the extended base CD over 2. OE equals to 5 units in itself according to what is given in the question. CD equals to X, it is the line segment that we are looking for in this question. and again O equals to 5 and CD equals to x over 2. So in total, those two sides of the equation are equal to each other. So in total, we found out that the area of the green triangle against CO equals to 5x over 2. But we only found out that the area of the green triangle CO equals to 14 square units in size. So we can write here that the area of the green triangle CO equals to 14 square units in size. Those two sides of the equation are equal to each other. That is to say, 14 equals to 5x over 2. Here we multiply this equation by 2 and we found out that 14 times 2 is 28 equals to 5x. Here we divided this equation by 5 and we found out that the line segment that we're looking for, this equation, that is line segment CD, is equal to x. It is equal to either 28 over 5 units in this from terms of numbers. The length of line segment CD is equal to x is equal to 5.6 units in this length. Okay, thank you very much.